So just going back briefly to what we did, what we did the last day. We looked at this case of recording a sequential recording, okay? So we talked a little bit about both simultaneous and sequential recording, and we talked about the case where replaying gratings that have been made sequentially, so separately from one another, and we derived out a set of equations for that case. And we allowed for the fact that these gratings may have some phase shift. And we went and we actually looked at the case when we had H gratings and we had N waves describing the field inside the grating, but we neglected the second order derivatives. And we talked about the cases where we were very far off Bragg, the two gratings could not be replayed on Bragg or close to Bragg, or where they were both replayed on Bragg exactly. And we went through the analysis for those particular cases. And then we started moving towards the idea of the simultaneous recording. And one particular example was the case where we have boundary reflections. And this is where we ended the last day. And I said, if we've got two beams and we've got a sizable or appreciable reflection at one of the boundaries, the far boundary, in fact, we record a total of 6 gratings. And that these are mixed gratings. They're both transmission gratings and reflection, unslanted reflection, and also slanted reflection. So this gets quite complicated very, very quickly. So today, we're going to look a little bit more at the case of the simultaneous recording. It turns out to be fairly significant, fairly important. And in this case, we're going to talk about deriving the similar equations to the last day, where we had the H gratings. But now we're going to have this fixed phase relationship between these gratings, which are based on the fact that we've got these beams mutually coherent with respect to one another, and they're all coming in at the same time. So I'm just, again, coming to look at our group and some of the things we've done in our group. And one of the things we've done is terahertz technology. We've worked with very long wavelengths, 1 millimeter, 300 gigahertz, and we've actually built a confocal microscope at that wavelength. And just to say to you that the fact that the wavelength changes, well, the material properties will certainly change, and the technical properties, the quality of the sources and the cameras, etc., will change, but the electromagnetics don't change. So this is the great power of the electromagnetic modeling. That once you've got it figured out, once you've sorted it out, it's true for pretty much every wavelength going. Material parameters, technology will change, but not the fundamental EMAG. So in other words, you can make holograms, and you can analyze holograms for terahertz in pretty much the same way as we're doing here. And we can do it in ultraviolet and infrared. Okay, so the sequential gratings, and we had the example there, the boundary reflections. So we mentioned that there's got multiple recording, there's always the possibility of saturating the recording material. So once we start recording more than one grating, the responsive material is going to be split between the different grating components that you record. So in the case of the boundary reflections we're recording, we are forming these other gratings, and therefore some of the dynamic range of the material is being converted into these spurious gratings. And we may argue that there's very little intensity in those spurious, in the beams recording those spurious gratings, but still we can have appreciable wasted dynamic range. So for example, in the boundary case, we were trying to record a single grating, we ended up recording 6. And so even if a small amount, even if 1% of the dynamic range is going into each of the others, we've wasted 5%. And fundamentally, what we're saying is there's going to be a limit to what we can achieve in that type of situation. We can't achieve 100% diffraction efficiency because there's always going to be some light which will be bled away by these other gratings. Okay. Single recording, this can also occur, as we'll see later, and the grating will be a K and higher harmonics of the K. And in the case of multiple gratings, let's say K1 and K2 recorded in a material, the higher order gratings will be of the form an integer times K1 plus an integer times K2. So we've seen this before, where these are integers. An example of such a case is given in the figure below. So here we have some examples of cases where we've got multiple gratings. In this case, we've got 2 multiple gratings, and they're both reflection gratings, and they don't share, they're far off Bragg with respect to one another. And if we do an angular scan, what we'll find is we'll get 2 Bragg conditions, and they're well separated. We've got some effects due to the material, and we may have some higher order effect. We've got here the 2K1 minus K2 and the 2K1 minus K2. So these are multiple scatters, and the higher ones will come here. But we've got this very strong Bragg effect, and these higher order terms are relatively weak. This shows the transmission, the actual measured transmission in this case for an experiment carried out. Okay, suppose we replay the sequential grid at the common Bragg angle, but at one of the other recording on Bragg angles. On page 5, we will then not only get one strong beam, but two strong diffracted orders. So we can come down here, and here's a situation where we've got two sequential recordings, but they share a Bragg angle. And if we replay this, yeah, we can get a replay like this. We can get scattered to this beam. We can then get scattered to this beam. We can have another beam down here. So we can have multiple scatter effects. Yeah. So if you've got multiple gratings, you've got the possibility of light being scattered into this is our reference beam, our wave 1 and our wave 2. So multiple scatter, direct scatter is going to be important and multiple scatter is going to be important. And of course, we can have mixtures of reflection and transmission gratings. So we can replay here a reflection grating, and there can be scatter from that reflection beam back over here via this reflection grating into this. So this beam here can be scattered here, yeah, and can be scattered up here. We can get multiple pathways, and we've got to think of these gratings as potential pathways, and multiple scatters have lower probability of getting light into a particular beam, but that doesn't mean it has zero probability under particular conditions. Back to our original general formulation, we can write for this case the following set of equations, and we've assumed now we've got no phase shift between these gratings. We've got these things that we introduced previously when we talked about this sequential recording where we had a phase shift between the two. We just assume we have no phase shift, but we do have off-Bragg parameters. So in this case here, we've got three coupled first order differential equations. We've got three potential beams, the 0, 0, 1, 0, and 1, minus 1. And we've got these two can be off Bragg. And we've got coupling here between the 1, 0 and the 0, 0 and the 1, minus 1. So there's direct coupling between this and these two. The 0, 0 is only coupled to the 1, 0, and the 1, minus 1 is coupled to the 1, 0. And we would choose this. We would say that we only need these particular waves because all the others are far off Bragg. So on Bragg, and this would have come from work by a man called Case back in the 70s, he derived an analytic expression for this. He solved these differential equations analytically, and he came up with a set of equations which looked like this. And you can say these are slightly more complicated than the ones we had previously. Yeah, this was for the on Bragg case. These are shown as functions of nu, grating strength, and we've got the grating strength associated with the different beams, and we've got a combined grating strength. So this is two gratings, and this is nu on edge 5. It's interesting to note that although putting in at beam 1 is on Bragg for beam 0 can get only to a maximum value of 50%. Whereas beam 2, the maximum diffraction efficiency is 100% when we choose these two to be equal to pi over square root of 2. So again, go away and have a look at this formulation. Yeah, go back and look at the diagram and look at the formulation here, and you see these relatively strange type of effects. Yeah, where we're on Bragg, but the best we can do is 50%, and another beam can 100% with judicious choice to grating strengths. Beam 2 is present at recording, and so is not exactly a spurious wave. However, we now examine the case of two sequentially recorded reflection gratings, this is on page 5, which produce a transmission direction spurious beam. Yeah? The case of two sequentially recorded reflection gratings which produce a spurious beam which is transmitted. Yeah? So this is, again, just showing you the complexity of what can happen here. In practice, such a multiply scattered beam is typically small. There isn't a lot of power in it. But again, if you're trying to get this thing as efficient as possible, and you forget or you don't worry about the fact, you do a model where you put in your reflection beams, but you won't put in your transmission beams. First of all, if you do the experiment, you'll see a transmission beam. And second of all, and more importantly, if you design it for 100% efficiency, you're not going to get 100% efficiency. You can't. A case does exist when these beams are large. So large here, we talk about 3 to 4%. Again, this would be associated with a reflection at a boundary. Okay, so it's an extra loss equivalent to a reflection at a boundary. That is when not only is there a common Bragg angle, but the two other recording angles are also close together. In this case, A minus 1, 1 and A1 minus 1 are spurious and significant. Results are shown on page 8. It is important to see that these beams exist without any direct K coupling. There's no actual grating vector, yeah, directly from our input beam or replay beam to produce power in these beams, but there is the possibility of light being in those beams. So 3 superimposed gratings. So we recall our formula in this case. We now have a average permittivity, we've got some modulation, and we've got 1 here to 3. So we've got 3 of these gratings. We've got an incident beam. We've got our flow K condition, and now we have an integer K1, an integer K2, and an integer K3. These are all the possibilities that we can get for diffraction order. So our input plus all of these. And of course, this could be 0, this could be 0, and this could be 1. We'll be back to a simple case that we had before, direct coupling, but we can also have these multiple couplings. And in general, as I said, they're not going to have a lot of power, but sometimes they can. The field expansion inside the grating is given as this. We now have sum over 3, L, M, and N. And we have here a theory, an experiment, a comparison of a case when we have multiple gratings. And again, you can go to the book, Sims book 7.4-5. Experimental measurement and index match tank. So we got rid of our boundary frictions. Theoretical result for 2 transmission gratings, sequentially recorded, and this is in silver halide. So our analysis up here, substituting that in, is going to give us the following set of equations. So we now have, here's our first derivative, here's our off-Bragg parameter for that beam, and we got coupling here, showing the coupling here for all these beams with some phase shifts allowed in here if these gratings are not in phase or they don't have a 0 phase shift with respect to one another. We have our obliquity factors, our off-Bragg, our dephasing parameter, and our coupling constant for each one of these gratings. With in orders from each grating, they will be into the cube equations. So we have 3 gratings simultaneously recorded. Here's our K vectors. Here's our beams, the simultaneous recording. And we have this relationship between these two, actually the way it's drawn. This extra, this one here, and this one here. We've got these relationships between the lot of them. For this case, replayed on Bragg with the 0 beam, each wave is coupled to 2 others. Okay? And so if we ignore any desynchronization between these things due to the psi phase relationships between the gratings. And so this in shorthand notation, the differential equations are like this. We have this obliquity factor, the first order rate of change. They're all on Bragg. And then we have a coupling to Bj, where we have 3 equations. So B0, B1, and B2 are the 3 waves. Ci is the slant factor of the ith wave, and kappa ij is the coupling constant between the ith and the jth wave. If A0, A1, and A2 are the amplitudes of the recording beams, then if we have fixed ratios, we will have perfect fidelity of reconstruction. So if during recording the 0 beam is much stronger than both the 1 and the 2 beams, then kappa 1, 2 can be ignored. And both efficiency, so we won't get a good grating between these 2 during exposures. Both efficiency and fidelity decline as the relative strengths of the cross grating increases. For simultaneous recording, changing the phases of the input beams has little effect at replay. For sequentially recorded beams, the phase of the beams during recording are thus the phases of the grating. They will affect strongly the power distribution of the beams. So we have this dependence on the phase relationship between the gratings. And we can change it. If we can phase shift one of the recording beams, we can change what we get. 3 gratings simultaneously, we replayed off Bragg. Unfortunately, there is another problem. K01 and K20 will be volume gratings, whereas K12 may be thin. So we have this multiple recording, and we can have a strong grating between the strong beam and 2 weak beams. We'll have relatively strong grating. Between the 2 weak beams, we will have a grating vector, but it may be a thin grating vector. It may produce a thin grating. So we have a mixture now. We can have mixtures of transmission and reflection. We can have mixtures of thick and thin gratings. And again, we're emphasizing here, thick and thin have nothing to do with the actual thickness of the layer. In this case, we've got all these gratings in exactly the same layer, but one of those gratings is weak. And because it's weak, its diffractive effect doesn't have a very strong Bragg effect, and it's effectively a thin grating. Now, if we do rigorous analysis, it doesn't matter whether it's thick or thin. But if we're making approximations to analyze what's going on, it will. Okay, and this one will not be very selective. An example is given on page 12. For this case, all the recording beams have equal strength to ensure K12, kappa 12 is strong, so the K12 is as strong, if you want, as the other grating components. They're all thick. The recording angles, we give a set of recording angles here. 3 and B4 are the spurious beams. 5 and 6 are the higher order spurious beams. The existence of the thin grating can be confirmed by making a recording with beams 1 and 2. A theoretical fit to these beams is also present on page 12. So we have a series of analyses, yeah, here, which show the effects with different types of gratings. And if you want to read more,
Professor Sheridan, excuse me.
Yeah.
Yep. There is a question from Vasily Lisnichi who asks, what is fidelity or fidelity?
So when you replay it, you get back essentially what you expect. So if we talk about recording a sinusoidal pattern, yeah, then we would talk about, we would expose with an interference pattern, and we'd expect to produce a single sinusoidal pattern. But if we have spurious gratings, we're not producing a single sinusoidal pattern. And in fact, we may be producing a grating which is a completely different K value, okay? Now, the weaker the spurious beams, so there's many aspects to fidelity, but the aspect I'm talking about here is the fact that we want to record, for example, 1 grating or 2 gratings or 3 gratings, and we're producing more gratings than we want, okay? Or we want to produce 3 gratings and we're only actually producing 2 gratings, which are thick gratings. So it's the exposure and what one wants from that exposure and what one actually gets. So a classical example of loss of fidelity would be if we had a nonlinear material and we would want to record a single sinusoid and we would in fact get harmonics. Now, you have to be careful about this concept of fidelity because fidelity is usually used in terms of sound fidelity. So we want to hear music and we don't want to have distortions on the music. Here we're really talking about the fidelity of the spatial frequency recording and the relative strengths of the gratings. Does that help?
Yeah, thank you. Yeah.
And one of the issues that arises here is that the fidelity, however, is also linked to the idea of replay. So when we replay the grating, we might expect certain diffraction orders because typically we want to have some functionality out of the device. And in a certain level, no matter what we record inside, as long as we get what we want, we're happy. Okay, so if we expect to put 1 beam in and get 2 beams out that are both 50% diffraction efficient, and we're prepared to live with each of them being 45% diffraction efficient, then if we get 45% in each of the 2 beams for a particular replay angle, we would say, oh, we've got good fidelity. Yeah, so there may actually be spurious gratings in there, but if they have no effect on the result, we may still be happy to call the grating or the holographic optical element, we may, as describing it as being high fidelity, good fidelity. This is the slight confusion because typically we're interested in the efficiencies. So as long as we're getting the efficiency we want, we don't care too much about the fact that there's a lot of different gratings in there. We in our understanding, however, we are interested in having all these different coefficients. This is a graph I actually showed you previously where it says to you, look, if I replay this thing, yeah, if I compare, first of all, the comparison to an experiment, they tend to be quite good for simultaneous exposures. But we can go back, we can look at our experimental data, and what we can do is we can see, ignoring all boundary reflections during replay, we'll actually see all these higher order components that I talked about. And these higher order terms, we want these 2, for example, but all this higher order stuff indicates a multiple scatter and effectively a loss of fidelity. So this is what I say about the replay. If we have 2 gratings and we get second order diffraction due to this K1 plus K2, we can interpret that, or we can say, well, we wanted K1 and we wanted K2, but we don't want the effect of K1 plus K2. And therefore that effect, which is natural, it's normal, and it's physical, we would still describe as some sort of a loss of fidelity because we don't want it, yeah? So even though it's there and we expect it to be there and we know it's going to be there, in terms of the functionality, we don't want the effect. So spurious transmission response, experimental and theoretical results are shown, and note the high diffraction efficiency of the T1 value. Gratings due to internal boundary reflections during recording. We mentioned this the last day. If recording is done in air and not index matched, for T polarization at a glass area boundary, we're going to get an amplitude scatter, which is going to be about 0.2. And 0.2 squared is equal to 0.04. So that's 4% of the intensity. But we've got 20% of the amplitude. 20% of the amplitude of the light crossing will be reflected. And again, we just note that if we have a beam which is 0.2, and we've got another beam that's 0.2, and they interfere with one another, we will get a fringe which will have a maximum amplitude value of 0.4. And if it destructively interferes, it's going to be 0. So we have a sinusoidal pattern with an amplitude value of 0.4. If we take the intensity of that, the intensity of that is 0.4 squared, which is going to be 0.16. And that's equal to 16% intensity. So we've got to be very clear and very careful when we have interference, because although we might only have 0.2% of the amplitude reflected, which is 4% of the intensity reflected, when we get interference, we can have a fringe which has a maximum which is equivalent of 16% of the intensity. So of the light crossing will be reflected, ignoring multiple scatter effects. This means that, so we don't worry about the light bouncing back and forth between the two boundaries. Typically, one boundary of the hologram is going to be on a material which has a close refractive index like glass, a substrate like glass or plastic. So we only worry really about a reflection of one boundary, and often it depends then on how we actually expose the beam. This means that on recording, one strong grating with two beams and two other beams traveling backwards will also be present. This is this diagram I showed you at the end of the last lecture. 4 waves simultaneously will give 6 gratings. Recording at one wavelength and replaying at another, the angular scan shown on page 13 was found. On page 15, the 6 evil diagrams for the diagrams are given. So we have, these are 6 that I showed you before with back reflections, and we can go away and do angular scans, and what we see is a whole range of different types of capabilities or effects, and we'll talk a little bit more about that graph in a second. Holograms have diffuse objects. So now we've talked about making art holograms. We've talked about making, and we typically in art holograms, we want to have a clear picture. And we've talked about recording multiple gratings. And of course, if we take a hologram of an object, we're going to have a spectrum of plane waves, and we're going to be recording the interference pattern of a spectrum, a continuous spectrum of plane waves. But we can also have objects which are diffuse objects. So the light coming from them is, if you'd like, very, very spread out between all the various diffraction orders. And we can go from, for example, using diffuse fields to record things to going to having sharp plane waves to record things. And what you typically see is a blurring of the response. You can make diffusers, holographic diffusers as well. And sometimes even you want to have a reference beam which is diffuse, because you make these sort of like very broad band type holograms, but that means they're actually robust to replay in terms of art holography in particular. So carrying out sort of a set of experiments and increasing the number of recording waves gives the results shown in 16. All the beams have the same intensity. So if we go away, this diffuse object, we would imagine having a whole little set of point sources here. We're not talking about necessarily randomizing them in phase, though that could be the result. And having some, and what we see is that as we go from a single source to multiple sources, we'll still retain some Bragg type effect selectivity. But in general, we're going to have a much more diffuse and low diffraction efficiency from the device. Yeah. So, but this indicates 2 things. One is we're still going to get some Bragg type effect. We'll still get some sort of selectivity. And again, please, I note here to go to 7.6 and 7.6 in SIMS, and you'll be able to see a lot more information about this. I'm not going to stress this because a lot of these experiments were done in dichromated gelatin or in silver halide. But again, all of the results we're given, all of the theory that's been shown, yeah, here you see a comparison, a continuous curve, a numerical curve against experimental values, the dots. So all of these theories work. Okay, they're of practical value, even for quite complicated situations. It can be shown that for a small number of lenses, independent of their apertures, the side lobe structure disappears rapidly. However, 70% efficiency can be achieved with such gratings in the dichromated gelatin. Let's examine the case of recording N gratings, first sequentially with a strong reference beam and N weak beams. Yeah. So often, and what we're trying to model here, what we're trying to get a handle on is that typically we're going to have an object, and the object is going to produce scattered plane waves. And in general, each one of those individual plane waves is going to have a certain amount of power, but it's going to be relatively weak, for example, compared to a reference beam. So typically we might take that light from the laser and we could split it in half, and half will hit an object and come to a plate, and the other reference beam then will have 50% of the power. And the object beam, any of the individual plane waves associated with that object beam, are going to be weak relative to the reference beam. So we're going to get strong interference patterns between the reference beam and each one of the weak plane waves coming from an object. but we're going to get relatively weak gratings between the plane waves coming from the object, okay? So we'll have a diffracted field, but in general, we're going to have a weak effect there. So this is trying to get a handle with, let's say, something a bit more complicated. Okay, this may also be the case, for example, if you're trying to do something with holographic storage, where you put light through, for example, a spatial light modulator, and you're going to get light coming out in a set of diffraction orders. And those individual diffraction orders are going to be weak compared to a reference beam. This will generally be the case. And we may tune our reference beam. We may try to balance the light so it's got a strong diffraction interference pattern in our material. But the individual plane wave components are still going to be relatively weak. Okay? So if we have an on-Bragg replay here, we're going to have the input beam, and we're going to have a sum coupling to a lot of these AI, and these are going to be individually weak. And then for each one of those beams, we're going to have this and this. And again, we've assumed we've replayed this exactly on Bragg. If all the gratings are in transmission, okay, and again, that's an assumption. We said before, we can have situations where we produce reflection gratings or even spurious coupling, which produces light in the diffraction field. Then we can take this set of coupled first order differential equations and we can write down analytic solutions that the A0 is going to be cosine. We've seen this before. And the AI is going to be given by a kappa I, the coupling constant, which of course is proportional to the index modulation, this N1, times a sine wave with some scaling. So we've got analytic expressions where this L squared is given in this term here. Okay, this is just a normalization type parameter. So we've got analytic solutions for every one of the beams. And again, this indicates why art holography works. Yeah, because the transmitted beam is transferred into all of the diffraction beams, and it's transferred to all of the diffraction beams in proportionality to the strength of those gratings, and the strength of each individual grating is proportional to the actual intensity or the field, in fact, in those individual beams. So although this is very hand-waving and not very, very detailed, it is rational, it is reasonable. The analysis we've done is reasonable and is consistent. So basically, art holography works, and it works for this reason. For in-simultaneous gratings, each grating recorded by beams of amplitude A1 and to AK, this will mean that your kappa IK is given by this product between these two, and the differential equations are given by this, and we've got our fields here associated with the beams, yeah, appearing here in these coupled equations. And one method of solution is Solomon-Cook adds in some extra terms which are assumed only mathematically important. So you add in some extra terms, yeah, and you can set them to 0 later, but you do it so as to make the forms symmetric so that you can find solutions. And for transmission grating, you get the A0 varying like this. And for the diffracted beams, you get them like this, in the case of sine squared. Okay. And this L is the normalization type factor, and the gamma is given by this form here. So you can define a total efficiency, this is adding together all the diffracted beams to get the total efficiency, which is given by this form here, where R is this term. Now, this is very, lots and lots of mathematics. But again, the point is that you can start off with these very relatively simple expressions and these expansions in terms of number of gratings, etc. You can make assumptions about the relative strengths of the individual beams recording these. You ignore cross terms between the weaker beams, and you can actually come up with analytic expressions which will give you a feeling for what is the practical maximum diffraction efficiency you can achieve in these very complicated situations, which would correspond to actual recording of real world fields. And you can show that the total intensity of the object will vary depending on your assumptions regarding the number of gratings and the relative intensities of the beams and the angles at which the beams come in. So again, Sims talks a little bit more detail about this, a little bit more about the derivation. What's important for you guys is to see that this is completely consistent with all of these types of analysis can be shown to be completely consistent and to predict physical reality. Both models for insequential and in-simultaneous gratings assume all gratings are thick and ignore spurious waves. Only wave present at recording can be recreated. And this essentially is what we talk about in relation to fidelity. The importance and that they're recreated proportionally as strong as one another. So if I've got a beam that's twice as strong as another beam, when I get the diffraction, that ratio, that proportionality is retained. So we get a valid image reproduced. The importance of including these terms has led to development of the spectral decomposition theory. Both the repay light and the gratings are assumed to have continuous spectra, one of spatial frequency components, the other of grating components. And this leads to an infinite set of first-order integral differential equations relating all the waves. Now, if you've got some variation of the grating in depth, you're typically going to be solving this using run-cut method, not the state space. You can still solve these things with state space method, but then you've got to turn the grating into a set of layers and assume that the variations, for example, of the kappa and the off-Bragg parameters are uniform within those individual layers, and then you stack those individual layers so that you multiply the individual matrices associated with each layer. You solve for the field inside, and then you match the field going into the next layer. You linearize. By sampling the two spectrums sufficiently, the replay spectrum and the grating spectrum, and carrying out the calculation numerically, results can be produced for lenses, diffuse objects, and general holograms. So you can go all the way. And in terms of, for example, spatial light modulators used to calculate pages, this would be the way you'd approach it, with a fundamental grating vector associated with the period in the spatial light modulator if you're doing something digital. And of course, again, the intensities in the beam would also be then governed by the gray levels associated with the individual pixels on the spatial light modulator. Some analytic results can also be found. And the reason we like these analytic results is we can test what's happening. We can test the linearity or the fidelity of our recording material. We have a way, we can go back to some simple expressions, relatively simple expressions. And I know this expression here looks fairly horrible, things like this fairly horrible, but compared to the other alternatives, you run numerical programs over and over and over again, and you've no way to check really whether you put in a minus sign somewhere wrong in your code. So we got a summary here. We have a short time, and it's very short time, very compressed here, covered a great deal of ground, which is necessary if a true picture of what is happening inside a grating is to be built up, and going from these single sinusoidal gratings to much more complicated patterns inside the grating. Examine spurious waves and sequential gratings and derive some analytic formulas for them. Examine the case of 3 volume gratings for the sequential case and the simultaneous case. The multiple gratings recorded due to boundary reflections were examined. Images for diffuse objects were examined, so broad spectra, and theories presented for the recording of in-sequential and in-simultaneous gratings. And finally, elimination of both these theories, the limitations of both are pointed out, and a general method, the spectral decomposition method, proposed. Okay. Now, I'm sure you're all sick and tired of sequential gratings, okay? And now we're going to go on to something which I think is very interesting. I think should be interesting for most people. Now, of course, we're always hoping that we've got a perfectly nice material. And I mentioned to you the idea of going to these non-latent materials or self-processing materials. I mentioned this briefly, which we're going to talk about when we talk about photopolymers. And these are materials which we don't have to chemically process once we've actually recorded our grating. We expose, and typically we don't have to do anything, or we have to shine, for example, a uniform beam to actually remove any unbleached dye, or to, and therefore to make the material completely inactive. But we don't have to do very strong interventions. So for example, with dichromated gelatin or silver halide, there was wet chemical processing involved, which could lead to a lot of shrinking or swelling or variation in the actual composition of the materials. And all these different effects, either due to the absorption of the dye or due to shrinking or swelling, would cause variations in the recorded grating. So if we want to record a sinusoidal grating, and we want the sinusoidal grating to be everywhere uniform inside the material, so that when we replay it, we get reproduction of the diffraction orders that we want. We don't want to have any variations caused. We don't want the material to be changing that sinusoid into something else. The classic is non-uniform, where we produce harmonics of the grating. We don't want anything like that. We don't want spurious gratings. Spurious gratings also reduce the fidelity. But even in a material like photopolymer, which is a relatively linear type of material, we're still going to get effects which are going to vary the off-Bragg response in particular. It's also going to vary the on-Bragg response, but let's concentrate on the off-Bragg response. The presence of variations in either the amplitude, the profile, the refractive index modulation with depth, and we mentioned previously the idea of light being absorbed by the dye, and therefore we wouldn't have exactly the same intensity at every point in the depth inside the volume, or of the period of the grating with depth. And this could occur because of some shrinking or swelling. And in any material where we've got some sort of a change in the actual density of the material with depth, we can get some shrinking or swelling. Or, as we will see, variations in the average index with depth, therefore changing the optical path with depth. All of these things will produce non-uniformities and loss of fidelity when we replay this grating structure. So we're going to have a look at these non-uniform gratings. Once again, I emphasize the introductory nature. So you need to go away and have a look at SIMS. And of course, SIMS was published in the early 90s, gives very good, solid, accepted theory. There's a lot of work been done by a lot of people since then, mostly dealing with, let's say, cleaning up particular issues. And we're dealing here very much with holographic materials, so materials where we have a weak, relatively weak variation of modulation. And again, I mentioned to you as a number that we've got very strong materials now that go up to about maybe 0.1, 0.2 of modulation refractive index, but your more standard materials are going to be at about the 0.1, 0.01, 0.02, 0.04. Okay, so you need to go away and read the stuff that I've given you. But we are beyond covalent now, and we're going to tie in with Gaylord. Once again, I must emphasize the introductory nature. Yeah, in most cases examined we're primarily interested in the two-wave grating case. Okay, but we've shown now how we can go, but so we'll only be looking at trends in the angular and wavelength responses of the grating, and general analytic solutions do not exist. This is one of the tricky points here, that we've been spoiled with our sines and our cosines. In many cases, we're going to end up with too many coupled wave equations, yeah, too complicated coupled wave equations in this case, or variations which don't lend themselves to the derivation of analytic solutions. There are some, but usually we have to assume some very specific restraints on the variations of the grating with depth. So in general, analytic solutions don't exist. Happily, because we got wrong Cutter methods, we can relatively easily solve these things with varying periods and varying modulations with depth. And we'll have to resort to numeric analysis. Also, in general, optimization techniques are used to find out what a grating profile might be. So if you don't have an analytic solution, how do you actually find out what the cross-sectional structure is? What you typically do is you measure the off-Bragg response of the grating, and then you use an analytic method to produce a predicted, you guess values, and then you put those values into your numerical scatter model, your coupled wave equations, and for various types of variation, you predict the shape of the off-Bragg curve. And when you find a set of realistic parameters that produce a fit to the experimental curve, and there's some ambiguity here, you say, well, now I know what the cross-section profile is. This is inverse scatter. And typically there won't be a single best fit, because you're going to have noise in your system as well and all sorts of difficulties. In simpler cases, it's easier, and with given some a priori knowledge, for example, if you know where the shrinking or swelling might be, or you know what the average index variation might be from other physical effects, then you can get a reasonably good fit. And often these things involve some sort of a search routine. I talk about optimization there, where you give it some starting value, and then the program runs independently, and it gives you some sort of a best fit to the experimental curve. We might talk a little bit more about this later. Or you get some student, and the student sits there plugging in values until they get what they consider to be a reasonable fit to the results. So that's what I mean by the optimization. This usually means someone tries a lot of different values and iterates to a solution. This is an inverse scatter approach, and in general, more than one type of grating can produce exactly the same output, but luckily, yeah, one of them is more physical than the others. So we hope that by the end of the lecture, you will be able to recognize the effects of nonlinear recording and know the various contributions they make to the output response of these various gratings. So the classic responses is a taper. So if we've got two beams coming in and the light's being absorbed, by the time you go from the input side for the two beams to the output side, enough light has been absorbed that basically the exposure has varied exponentially, which means that we get a stronger exposure at the input phase than the output phase, and we get a grating modulation, which is going to vary in the same way. So we have a sinusoidal variation in amplitude. It's not going to be so simple as an exponential decay. However, it's a pretty good approximation for a lot of situations. if I then replay, if I look at the off-Bragg term, what's going to happen? Well, if I've got a perfectly uniform grating, I get this sink-like function. We have a maximum and we have zeros, and we've got side lobes that are nice and symmetric. And again, I explained to you that you get this zero, you get the Bragg effect because the scatters from all the planes, you know, the periodic structure, all add together constructively. And similarly, we get a zero here because all the light scattered by all the different planes add destructively. So we get nothing diffracted. If we introduce a non-uniformity in our modulation, then what that means is that the amount of light scattered from different parts of the volume don't exactly balance or cancel one another. They don't cancel one another. And the net result is that we no longer have a zero here. We have this, we still have this central type structure, but we have this much slower roll off without these clear nodes, which means that as a filter, we have a worse filter. If this would be, for example, a variation of angle or, for example, wavelength, we would be able to say that that filter stops everything coming in, diffracts nothing at that particular wavelength or particular angle. And now, because of this effect due to the exposure and the absorption of the dye, we no longer have that nice, neat zero. Okay? Another effect, and I like to think of this as an accordion musical instrument type effect, is where we have a linear, and this is a linear chirp. So an exponential taper and linear chirp. It turns out there are analytic expressions for these two particular cases, but they're not very nice. They're complicated, relatively speaking, to sine. In their period at one side than we do at the other. So this typically happens due to density changes during exposure, due to the exposure. So you start off with a homogeneous medium, you push in your light. At the front end, for example, there's a lot more light and maybe there's scatter. And so you have some variation of the density of the material and perhaps the average refractive index. And what that leads to is a longer optical path length at the front, or an actual physical swelling, which is a longer physical distance. And swelling is usually accompanied by some reduction in density. So we have to allow for this. The net result in this case is that we no longer have, if we had a perfectly uniform grating, we'd have a very clear on Bragg with this nice, exactly the same as we had here, with this nice uniformity. And now what happens is we have now got something which is spread out. We have, if you'd like, different wavelengths are reflected on Bragg at different parts of the grating. Our K grating, a grating vector, changes depending on the depth. So now this is a very simple case. This would be a reflection case, and we've got this very nice. So this is not the unslanted transmission, of course, but this is a reflection case. And so what we have is we've got a broad band reflection. And so what we see is that the strongest diffraction will not necessarily be at the point at which we record it, because we've had some change in the material, possibly post-exposure. But also we've got a broader response, because now we can get different wavelengths being on Bragg at different points in this structure. So this is a modulation, and this here is a chirp. And we can in fact produce modulations which actually reduce the side lobes. We often talk about apodization, where we produce a refractive index cross-sectional profile where the modulation varies across it in such a way that we reduce the size of the side lobes. Okay? But this may be accompanied by some broadening of this band. And chirp, again, we can have different effects producing this. And usually, in fact, in a general grating, we're going to have both of these things happening at the same time. Okay, so non-uniform volume gratings. There are many processes by which a non-uniform grating may be formed. Loss during recording is perhaps the simplest way, general absorption. And as I said, I could attribute this to the dye. However, the non-uniformity is created, it is possible to break it up into about 4 different components. So taper, this describes the case when, due to loss, for example, the dye, the modulation varies with depth. And typically for a slanted grating, the index with depth, so we have to have a slant, because in the unslanted case, of course, we have a constant index at any slice across X. For the Z value, we're going to have a constant index. So we've got slanted grating, so we've got a sinusoidal variation. The index with depth varies like this. So we have an envelope with this damped modulation. So this here now is our refractive index. We have an average value, we've got a maximum minimum, and then we've got this taper. And of course, in our uniform case, we would have no taper. This gamma parameter here will be 0, and we have the same sinusoidal value all the way across. In this case, our index now is written by this term here, and it's all the same except for this loss factor here, this attenuation factor. that's producing this envelope. So of course, if we let this equal to 0, we're back to our uniform case. So the weaker the taper, the closer we're going to be to the uniform case. Chirp. This describes the case when the period of the grating, this period varies with position inside the grating, and therefore so does the grating vector, because the grating vector is 2 pi over the period. So if the period varies, the grating vector varies. For a linear chirp, one in which the variation is directly proportional to the position inside the grating, we get something which looks like this. So again, we have linear proportionality, and as we go in Z, the period gets bigger. We have a constant modulation. Here's the refractive index. We've got an average value, a maximum, minimum, this oscillation, but the period has varied. In this case, the index can be written as follows. So we have N of Z is average, the modulation, which is constant, and then a cosine of K dot R. And this K here, we could imagine as the DC, or the average grating vector value. And then we have a phase term here. And that phase term here is describing, taking account of the fact that our period is varying. We have a relationship between the phi and the grating. So our grating vector at any point in Z is given by this DC, our average value, plus the rate of change of phi with respect to Z times this unit vector in Z, because we've got this relationship between phase, frequency, and phase, okay? For a linear chirp, this phi of Z is a phi 0 plus phi 1 times Z1. It's linearly varying, and our grating vector is going to be Kz plus phi 1, yeah, this modulation of the phase. And this phi will be a constant phase shift. So we've got two of them, the taper, and we've got our chirp. An average index variation, there may be a slow variation of the average index across the width of the grating, and this may be included as part of the grating modulation, perhaps a new K vector included in the calculation. This would be a very heavy-handed approach, although rigorous. Instead, it is noted that changing the average index will change the optical path length, so that the phase accumulated by the light as it propagates. Thus, light in the grating will effectively see, if we've got a weak variation in our refractive index, average index, accumulated phase in different amounts in equal lengths of the grating. This warping of the distance, the optical path length, will act like a chirp as the light traverses the periods with different optical path. So here we have our grating, and we said, look, if we look at this, we actually get this. This is the visibility, or the size of the modulation. We could describe this here as a cosine, but we've got it added to an average index that is varying, this green line. And what we say is that is equivalent in terms of this inverse scatter problem. This is equivalent for our purposes to actually a grating here where we have this chirp profile, where we have a bigger optical path in the middle where this average index is highest, and a lower optical path at the edges. And so what the light will see if it replays something like this, it will actually see a grating profile which looks like this to the light. Yeah. So the higher average index in here increases the optical path, and therefore effectively increases the distance, for example, between that point and that point, compared to that point to that point. Thus, the effects of average index variation are indistinguishable, and we put that in inverted commas, but relatively indistinguishable from those of chirp. And especially if we're talking about weak variations. And we're going to see this later. So we can, we can choose which one we want to do. And the more a priori knowledge we have about one or the other, the more information we'll be able to extract. In the above figures, we attempt to show the equivalence of two structures. Usually the effects of both types of variation are lumped together. Okay, so I just blew this up here. Yeah, so we have high average index, longer optical path length, low average index, lower optical path length. Non-linear recording. So this is our fourth thing, okay? And all of these things happen, and the mechanisms by which they happen depend on the material you're using. They depend on the type of material you're using, and which effect is more important also depends on the material you're using. And the reason we're so interested in this is because often we want to have highly selective elements. So for example, if we want to record multiple gratings, we want these multiple gratings not to affect one another. So if I replay one grating and I'm getting power in another, or I replay two gratings and I'm getting power transferred to one to the other, this extra light that's coming along is effectively a noise. So for example, in the case of holographic data storage, if I record 2 pages and I replay one page and I'm getting some scatter, okay, which is due to a different page, that is noise, and it's going to cause loss of signal to noise ratio, okay, which is bad. It means we can store less information. We can't pack them as closely together. So the other source is nonlinear recording. And this can occur when a material is overexposed. And this is an example. So there are many different ways in which we can get nonlinear recording, but this would be one particular example with which you should be familiar. And this is the idea of overexposure, okay? And the variation recording becomes warped or cut off, and this type of chopping is shown. So this is a saturation type effect. Here's our, for example, we had this archetypal linear transfer function, and we had a linear region where we put in a certain amount of intensity. So our input intensity is over here, sinusoidal interference. And if we've got this nice little green one, we put this through this linear response of material. What do we get? We get the following variation in our reflective index modulation. So we have intensity in, and we have the modulation of material out. And if we're in this linear region, then a nice sinusoid coming in here is going to give us a nice sinusoid coming out here. We've got good fidelity in terms of recording of the grating. We have a perfect sinusoid in and a perfect sinusoid out. Now, of course, there's an issue about whether we expose with a perfect sinusoid or how much control we have over the exposing light or the reference beam. There's always going to be some diffraction effects, but for the sake here, this is illustrating the effects of the linear region. On the other hand, if we put in a much higher intensity, yeah, and this again is supposed to be a perfect sinusoid, so we've got a perfect sinusoid but a very high intensity, then we're going to reach regions beyond the linear region. And what that's going to do is it's going to produce higher harmonics. And in the worst case, we're going to hit this region in the material response, and we can hit that for a number of different reasons, okay? But assuming that everything is static, which of course it isn't, if we come up here too far, then we're going to get chopping. Yeah, we're going to get this chopping here. Now, there's also an assumption here that we've got this average intensity in here and the material reacts instantaneously, okay, which it may not do. So there's a number of different effects here. We can have various types of cutoff and chopping. If you've ever done power amplifiers, you'd have seen curves like this for power amplifiers. The main point here is we've got higher harmonics, and that means we're going to have more grating vector components. More grating vector components. And we've talked about this before. We talked about having H gratings. In this case, all the grating components are going to have the same fundamental period. So we're going to have a K1 and a K2, and K2 is going to be equal to twice K1. We'd have a K3, which is 3 times K1. So the periods are going to be multiples of the fundamental. A chopped off sinusoid looking more like a square wave has a permittivity expansion with many Fourier components, or can be written as if made up of many gratings, each of different period and modulation. All these gratings couple to one another, producing a complex set of output diffraction orders. So again, we're back to this idea of having these H grating components, and they've all got this particular phase relationship with respect to one another. It's fixed, where Ki is equal to I times K, the fundamental. We've already noted in lecture 5A, I think that would be lecture 6 maybe, that if more than 2 waves are used during recording and several overexposed gratings formed, then we have this form here, okay, where each grating acts as a fundamental grating component. Let's now go back and look more closely at the case of an attenuated or tapered grating produced by a lossy recording. In a lossy recording medium, so we've got lossy recording, but we're assuming that when we replay, we're only replaying a phase grating. So we don't have a loss grating, and we've bleached the material, so we have no absorption when we replay. So we have phase gratings, but the structure, the modulation of the phase gratings has been varied by losses during exposure. In lossy recording medium, the 2 recording plane waves are given like this. So we have this decay, this decay caused by absorption from the dye, for example, or maybe scatter. So that's our 2 fields that are recording. So before we would have had just 2 plane waves. Now we've got the plane waves attenuated as they propagate, and they've got these angles associated with them. The total field is the sum of the 2. The intensity is going to be this, then multiplied by its complex conjugate. And what do we get? Well, we get the magnitude of this squared, the magnitude of this squared, and then we get the cross term. So that's our field, that's our total field. Therefore, assuming after processing our material is lossless, so it's a phase grating, we have a permittivity value which looks like this. And this alpha here, which appears in this permittivity now, is some combination. It's a combination of the loss due to the material during recording and also the angles of the 2 beams. because of course the greater the angle, the distance propagated through the material is going to be different for the different beams. So it's not just simply that we can use the absorption that occurs on the recording beams, we've got to allow for the effects due to the two different beams. And if we see if these two things are equal, we've got this plus this is 2, so you've got 4, you're going to have that times the cosine divided by 4. So it's not just full stop, yeah, it's a bit more complicated. Using our standard procedure, we follow first order coupled wave equations, and we can go away and we can derive this out. So this is just the exact procedure we followed. Here's our first order with a Blaubicki factor off Bragg for that L wave, a coupling constant, and here's our attenuation of the modulation, and that's defining the coupling. So this is our new coupling constant, and the new coupling constant is a function of Z. And again, we've got a single cosine, a fundamental, and so we're coupling up and down to the local beams. If we've got higher order components, we would also be able to couple to L plus 2 and L plus 3 and etc. So we have a kappa, which is a function of Z, which is given by this term here. For the two-wave unslanted transmission case, this can be solved analytically to give the following, that A0 is equal to cosine of a grating strength and effective grating strength. So it's a little bit more complicated because of this variation of the kappa constant with Z. And A minus 1 is equal to minus J times the sine of this effective. And the effective grating strength is given by this here. Yeah, it's given by this value here. That's the effective grating strength. You've got to be careful how we do this. But again, what we've actually done is we sort of found out an average across that thing, the coupling, the average constant across it. Okay. From this, we can see there is an effective modulation, and that effective modulation is given by this average, the average modulation. So we integrate this from 0 to D, the thickness, divide by D, and what we have here is we've got an average permittivity value. So all we've done is we've said if we've got this modulation, it's very nice, it's very handy, we're playing on Bragg, we calculate out an average index, and we can use our standard types of formulas, the cosine and the sine, to find our fields, diffracted and transmitted fields. So that's very handy. More general solutions for the two-wave case have been found by Kowaschik in terms of Whittaker functions, and Yoshida in terms of Bessel functions. So you can go away and go mad and have all sorts of profiles. And these are for general gratings and are complex. And you can go and look at the literature, go to Sims, and he talks about this. We're turning now to examine the case of chirp. Okay, so now above we had modulation variation, and now we've got a chirp variation. And we have a situation here where we show a set of fringes. We've exposed something, we've made a grating between two patterns, and this may be recorded with two spherical waves, or a spherical wave and a plane wave. So we've got but we've set it up so that the period in X is constant. So the period in this direction is constant, but the period in Z varies. Okay. And we can talk about slicing this up into multiple layers. Yeah, so the dashed lines will be multiple layers. And then in each tiny layer, we assume we've got a grating with a particular slant angle, a particular K vector here. So over that distance, we're assuming the period does not vary. And then we figure out what happens to the light that propagates from here to here. And once we get here, we use the two orders, the transmission and diffracted order, as the input to a new grating. So usually we only replay grating with one beam, but now we're replaying this one here with two beams. And again, we find out the transmission and the diffracted, and we go all the way across here until we find the output at this side. That's one approach we could use. We have a permittivity here now, which is due to this. So that's one lamellar type decomposition that we could use. And we've got a permittivity here, which is an average, a modulation, and we've introduced this phi variation instead. So we have a K which varies like this. And the coupled wave equation, and then we can go back and look at these things, using the standard method for lossless grating is going to give something like this. So we have a standard form which looks like this, where this phi now is related to this phi shift over here. Are we okay? Are there any questions? So we can typically solve these numerically. We can solve an equation like this numerically, where we allow, now this is X here, but this will be Z in my notation. So he's using X here as the thickness correction. Are we okay?
There is one participant with the microphone on.
Oh.
I want to please tell to put the microphone off. Okay. Mr. Beram Den.
Okay. So it's the hour, it's just on the hour now. Okay. So maybe I'll just stop here and we'll give everybody a few minutes to think up questions or something and have a drink or go to the bathroom. And we'll start again in 2 or 3 minutes, okay? So let's everybody just have a think about what we talked. If you've got some questions, write them in the chat and the moderator can ask me. And basically we'll come back together again in a couple of minutes. So we just have a little break.
Professor Sheridan, are you here?
Yes, yeah. I'm back.
Here is the question from Ekaterina Musikhina about if eval diagrams can be applied to the case of non-uniform gratings.
Yes. So I don't actually think I've done an example here. But for example, one way is using this idea I've got here in front of me. I don't know if you can see my screen, yeah? So in this case, where we've taken the grating and we split it up into sections, each one of these sections, each one of these layers would have their own eval diagram. And each one of these layers would have a different K vector. So we could imagine having different eval diagrams from each one. And then basically we'll be able to see how on brag or how off brag any one of these sections are for particular replay conditions, okay? And we've got to allow for the fact that after this layer, first layer, we now have two beams and they're both replaying this grating vector, okay? So the first layer is going to produce two beams and these two beams are going to be replaying the K vector, whatever K vector we have in the second layer, and so it will go on. So what we can imagine, for example, is that as the light propagates through this structure, what we're going to end up is more and more and more diffracted beams. They're going to multiply, yeah? So if we have one beam here, we're going to have two beams coming into this structure, and we could have four beams coming out of this second layer, and it will multiply as we go forward because we've got different K vectors. So what we end up producing is a spectrum, okay? So the effect of the multiple of non-uniformity is to produce this idea of a spectrum of K vectors, okay? So what we can do is we could think, for example, if we replay a structure, let's assume we have something like a lens. What we would say is that that lens structure has a spectrum of K vectors. And when we replay that spectrum of K vectors, we're going to be producing beams which are on brag and beams which are off brag. So for example, I've seen diagrams where what people have done is they have produced an eval diagram with an input beam, and then they've produced a whole set of different K vectors starting from that input beam. And each one of those comes to a different point. One of them maybe it comes onto the actual circle and the others aren't on the circle. And the net result is going to be a spectrum of spatial frequencies diffracted by this non-uniform grating. Do you kind of understand what I'm saying?
Ekaterina, I think that this question is addressed to you.
Yeah, thank you. I got it.
So, I mean, the eval diagram is clearest and nicest to use when you've got single grating vector components. And the whole idea with the eval diagram, if you like, what I try to use it for is to give a very clear sense of the description of the field inside the volume. Now, if you've got a spectrum of K vectors, you're going to have a spectrum of produced diffraction orders. And so the quantitative ability of the eval diagram, I won't say it's reduced, but it's certainly complicated. But you got this fundamental idea of the beams that are produced and them being on Bragg and off Bragg, or transmission or reflection. And the eval diagram should be able to show that to you. Yeah. Again, you might say, well, okay, suppose I don't have a single plane wave coming in. Well, then what I'm going to have is I'm going to have, if you think of the sphere, the circle, the eval circle, what you're going to have is you're going to have like a triangle, a segment of the surface. Yeah. A segment of the surface of the sphere. And that segment of the surface of the sphere says I have plane waves traveling in this spectrum. Okay. So I have all these possible plane waves coming to the circle. Now, I then have, let's suppose I have a single K vector. Well, for some of those beams, yeah, the middle beam, for example, you may be on Bragg. And for the outer ones on the segment on the surface, you're going to be off Bragg. So again, you can say, well, okay, this is the one that's on Bragg. These ones are off Bragg. Therefore, I'm going to have a difference in the diffraction efficiencies between the on Bragg one and the off Bragg ones. Yeah. So you can replay with a spectrum and illustrate it on the eval diagram for a single K vector, or you can have a single input beam, a single vector to a single point on the circle, and then you can have multiple K vectors, and all of those K vectors have to start at that replay beam, and then whether or not they touch the surface tells you whether or not you've actually got on Bragg replay. Now you could imagine a spectrum of K vectors where every one of the K vectors gives you a point on the circle. So you'd have an input beam, a lot of K vectors, and your output then would be a segment, a cone, a spread of grating, of diffraction components, all of which are on Bragg. There's direct coupling via the spectrum of K vectors to each one of those beams. This would be an example like maybe what you'd see, for example, for an object, an art hologram, where you replay with a plane wave. The grating inside is complicated, but you can treat each one as being relatively weak, and therefore we play each one on Bragg, and therefore abracadabra, out we come with the spectrum which is associated with the object. So we have a fidelity. I hope that sort of makes some sense to you. Any other questions? Okay, if there's no other questions, I'll just come back here again. We're talking about this chirped case. Yeah, and we've got an example here of possible sets of fringes where there's no variation in the x direction. So if you'd like, the diffraction angles inside and outside are unchanged by anything that happens in the z direction. But in the z direction, we're going to have different coupling as we go along in depth. So maybe here we're on Bragg and over here we're off Bragg. And we can break it down to lamellars where each one of these is an independent grating. Or we can treat it continuously as this idea of a phase variation, an average grating vector, and then a phase variation, as shown. And we can go away, and we write down a set of first order differential equations, where again now I would use z. Yeah, so I've got z noted here, so this should be functions of z, not x. So that would be a first order derivative with respect to z, that would be a phase with respect to z, and again a phase with respect to z. And we would solve these, all of these a's, of course, are the amplitudes, so they're functions of z. However, cascaded thin sections can be used as shown above. So if we don't go away and solve the coupled equations using Runge-Kutta, we can decompose the grating into a series of slices and use our two-wave analysis for each slice. And both are valid if we use enough slices. If we have, and this again is the step size in Runge-Kutta. So typically we have to choose a step size in Runge-Kutta so that we achieve good facsimile to the reality. And then we'd have this kappa constant, for example, varying with depth, or this dephasing parameter. However, cascaded thin sections can be used as shown above, and each section is assumed to have a constant grating vector, and each section is different, but can be modeled by a two-wave component. And then it just depends how many waves are replaying each layer. Each section will have a different transmission matrix, whose elements are derived by solving the coupled first-order differential equation for that thin section. And the matrices are simply multiplied by one another. you cascade. And again, this is just period X, period Z. This is just blowing up that figure so that you can see it maybe more clearly. General trends. We now move on to using a thin section decomposition matrix method to examine all the various types of non-uniformity for the two-wave case. So generally, as I said, you don't get these things separated from one another. You've got a more complicated situation. You will have modulation, and you will have chirp, and you will have maybe an average index variation, and you may also have some nonlinearity. So you can have all of these things happening pretty much at the same time, and you're trying to disentangle all of these effects. And sometimes an effect that can be associated with an average index variation, it can be associated with chirp, or it can also be associated with some tapering. They're not completely delineated or separated from one another. Sometimes the effects are very similar to one another, okay? You can have very similar effects between these different resources. And of course, all we can do effectively is measure the diffracted light that comes out of the material. We can, of course, slice it up and maybe look at it with an electron beam. And of course, that would be something very handy and very useful if we could do that to verify what we're doing. And we could use it to apply extra constraints on our analysis. But in general, we don't have that exercise. And every time we change the material composition to see if we can get a better result, we don't necessarily have the time or the energy or the resources to go inside and actually do something. So the parameters, the modulation and the grading vector and the average are allowed to vary with thickness. And note that although the shape of this changes, the polynomial always integrates the same value. So what we do is we introduce polynomial type variations on these. Now, for example, if we have taper, we may retain the exponential because we know what we kind of expect. But we can in general come along and we can express all of these things as functions of Z, and this should be really Z here, where they're all varying with depth or thickness. Note that although the shape of this changes, the polynomial always integrates the same value. So we talked up here about this idea of the average index. Yeah, this idea that we have an on-Bragg diffraction efficiency that we can calculate, and the off-Bragg diffraction efficiency is a function. It's not a function of the off-Bragg parameter. It's only a function of this effective grating strength. So if we go away and we take our grating and we replay and we get our maximum diffraction efficiency, we can use that maximum efficiency to come along and define this effective grating strength. And so typically what we do is we say, well, okay, we're going to change everything in our fitting polynomials. Whatever we do with our modulation, we're going to make sure that when we integrate it, we get the exact same grating strength. So we can pin it down in that way. It reduces the number of things we have to look at. So we do that. Excuse me. Sorry. Yeah, we do that. Excuse me now. Sorry. Okay, so we have this fixed. So far, we examined the same stage. Okay. We see that for linear changes of the permittivity, the zeros disappear. So we get this effect here. This is a transmission beam. So if we vary here, we've got these different polynomials. And again, as I said in my notation, I'd have Z here. And this is our average index, our grating vector. This is the average permittivity, the modulation, and the grating vector. And so we have a set of parameters here. We've got a C, B, and excuse me, A, B. Sorry. Yes, sorry. So these parameters, we can come along and we can find out the minimum number of parameters we need in order to describe what's happening inside the grating. So we've normalized the values, and we've made sure that, for example, our average index goes to a constant value. And if we allow the C to be 0 and we vary the B here, so we have a linear variation in our modulation, then basically what we see is our zeros, we have this on-Bragg value, but our modulation values, the zeros here disappear. And again, we've chosen this so that our effective grating strength doesn't change. If we vary our modulation with a quadratic form, then what happens is we have, so that's even function. So there's a balancing across the actual grating. We've got an even function. In this case, it's asymmetric. So we're going to get different scatter from different points in the depth. In this case, we've got something which is symmetric. And what we see is depending on the values of these, we're going to get different size modules, side lobes. And what we can see here, in fact, is that for these positive values, we're going to get an increase in the actual size of the modules at the cross sections, the side lobe sizes. But for negative values, we've actually suppressed the side lobe size, and we've got some increase in the width. So we can, but we've normalized it always so we have the same grating strength. So what we're saying here is that we can introduce modulations on the cross-sectional modulation value. Yeah, we can vary, we can change the cross-sectional refractive index modulation so as to increase the size of the module of the side lobes or to decrease them. Okay. But in general, we always see we have this broadening of the actual response. So linear or odd, we're going to lose the zeros. Even functions, we're still going to retain the zeros, but we're going to change the actual side lobe sizes. And the one you're going to see probably most frequently, and photopolymers that are reasonably good materials, is you'll see this loss of the zeros and a certain broadening. Okay. If we go to changing the period, okay, if we go to changing the period, we get this type of an effect. For a linear variation, we see this distortion. We still have our central value. So changing the period here, we get this. You remain to this unbrag, but if you see here, the width greatly increases. And if you look at that maximum power half width, that increases by a huge amount, even for very, very weak variations in the cross-sectional variation. And we can see here that this is for the linear chirp, and this is what we get for a variation in the linear average permittivity. And for judicious choice of these parameters, you can't really tell the difference. And similarly, if we have a quadratic chirp or we have a quadratic variation of permittivity, once again, we see that we get this variation. As we introduce the quadratic chirp, we change our on-Bragg value, where we get the maximum diffraction efficiency, and we also have this distortion of the side lobe structure. And we get the exact same thing for the average index. So these are very hard to distinguish. So parameter of linear quadratic chirp gives the same effect as the particular parameter of linear average, and the same thing for the quadratic. So these things are pretty much indistinguishable. So these are general types of characteristics you would expect to see as you vary these polynomials. For variations of the average index, the effects as expected are similar to those for chirp. Usually only the chirp is moduled. We assume a constant average and we lump everything that happens into the chirp. Next, we present some experimental curves which have been fitted using the above theory. So you do experimental measurements and you fit them, and fitting using the procedure I talked about before. The index modulation and the k-vector used are shown on page 14. So the actual variations. So you got the experiments and then the predicted variations which produce the best fits. Similar work has been carried out by several people, and it has estimated which part of the, for example, dichromatic silver halide process causes various types of non-uniformity. So again, it's a case of the more you know, the more you can constrain the search, and the more experience you have, the easier it is to find reasonable fits. And again, these are particularly extreme cases. With photopolymers, you don't see this level of distortion in general. However, it has to be said that sometimes people want to introduce distortions for particular cases. And I mentioned this business here about reducing the side lobes, a reduction in the side lobes by suitable choice of, for example, quadratic variation in the modulation with depth. Okay, you can reduce side lobes, and maybe there are situations where you want to reduce the side lobes. And this effect is essentially an apodization type effect on a filter. It's an apodization type effect. So we have here a set of curves. So first of all, some experimental curves, and you can see here, you've got your experiments and you've got strong distortions. So in this material here, you definitely have some sort of chirp happening, and you've got a distortion in the cross section. And again, you see here experimental curves with the fits. Okay, so you can achieve fits looking at these different parameter values. And what we've got over here then is we've got the values here. This here is the modulation. This here is the predicted taper. So using the method and fitting the results and looking at your position in Z, you're assuming that there's this variation in the modulation strength with depth. So inside the grating, you start off over here with this modulation, and as you go further and further, it decreases down here from about 5 or 6 down to about 3. Okay, and this 10 to minus 2. And the chirp, you've got a variation that looks like this. So you've got this measurement of the relative deviation. Yeah. So you've got the periods are going to be varying like this. You're going to have some variation in the fringe spacing, which looks like this as a polynomial. So we go up here and we just say, what have we got? Sponsor reflective grating with kappa Z and kappa divided by kappa 0 shown is, so this is an average value. And these results are produced using a Runge-Kutta integral method. And the accuracy in curve fitting is very good, but is only achieved by manual iteration to the solution. But now, of course, you can use more complicated software. And again, it's the constraints, the regions you search for, and a priori knowledge that helps you get there. Although we've only presented rules of thumb, these work quite well, and it would be nice if they're comparisons of experiments and theory, if the replay of the grating at one wavelength vary theta, and curve fit to estimate the parameter of variation. You can vary wavelength as well, and then vary the wavelength and check if the results. So you can do an angular scan with one wavelength and then move, change the wavelength, do another angular scan, and then look at the results you get for the two different wavelengths, okay? And see if they get as good a fit. Okay. That's our values. And again, you can look on Sims for more details. This is a simple taper modulation. And again, often people use decibels here. And so you see this theory and experiment, and you've got this very good grating here, and this grating which has got strong taper in here. And again, effects due to chirp. And again, this is a decibel scale. So this variation is there, but it's not as big as it looks. Angular variation. And again, here is more taper and experiments and theory without actual reflections from boundary conditions, and then the variation of the chirp and the variation of the taper. Okay, so these are quite dramatic variations. There would be a material in which you could induce lots of shrinking and swelling, but again, the methods work. You can do fits to experimental results. Another way to imagine what's happening inside the grating, we have also looked at the angular responses of the gratings. What about their wavelength responses? What does a modulation do to the filtering characteristic of the grating? On page 18, we examine the spectral components of a grating, the cross-section shown by tracing its Fourier transform. We can see that some modulation will produce large narrow components with low spread into the side lobes, a modulus for single scattered first-born approximation gratings. However, if your volume grating has many k-vector components which are strong and spread far apart, it will be difficult to imagine getting a narrow response. Okay, so this here is a very simple thing. It's Fourier based, and again, it's just to give you some insight into what's happening. Suppose we have this sort of sinusoidal grating. We can take a Fourier transform of a uniform. We get two delta functions. Suppose we have something which is apodized like this. Well, we have a rectangular here associated with cross section. We have a sinusoidal variation, and we've got some sort of a taper, and we've introduced this thing as a cosine, the central part here, the cosine, okay? And these would, multiplying these functions in space would give us something which would look like this. So if we assume this is a very weak, so transmittance function type analysis again, but again, this is supposed to be the zep of the grating. Fourier transform of this is giving a sinc function, and this is going to be narrow. Fourier transform of this is going to give us delta functions. Fourier transform of this is going to give us delta functions, but this is a big period, so these are close together. And so we end up with something which looks like this when we do the convolution of these two. And when we convolve this with this, we get something which is like two sinc functions on top of one another, which is going to result in something like this. And if we choose the separation judiciously, we can actually produce an effective reduction in the side-to-side lobes. And if we go away and we actually, instead of here, we multiply here by a cosine variation to produce this thing, which is the maximum in the middle and 0 on either side. If we come along and we just use something like a sine or a square root of sine or a sine squared, and we use Runge Kutta, and we don't do a normalization of the diffraction efficiency, what we see is that for the square root, we have worse side lobes than we do for the sine. And if we go to sine squared, we have a greater reduction of side lobe stride compared to the central part where we have a broadening. So this is just saying, look, we have Fourier ideas that we know from signal processing, which give us some sort of an indication of what can be happening. We can go away and plug in particular profiles, particular kappa. We can have kappa x varying in particular ways using these analytic functions, and we see the exact same type of characteristic for a multiple scatter case. In these cases, we note the on-Bragg diffraction efficiency is not normalized. Yeah. So in the previous cases, we would have picked this value here, we would have made sure that the normalized value was always the same. So again, this is just trying to give you some sort of insight into what's happening in these gratings. So the three responses in which only the modulation envelope has been varied are shown: a good envelope, low side lobes, apodization, we got high roll-off, should have the value of 0 at the boundaries. And many of this derivatives should be as 0 at the boundaries as possible. So when we want to smooth this thing, the smoother this apodization is, especially at the edges, okay, the better the reduction, we have a higher and a better reduction in the side lobe structures. And this is just from classical signal processing. Okay, you can go away and read it with Hamming and Hanning windows, but it's very interesting to see that these ideas transfer to volume gratings. Finally, let us look at a few unusual types of gratings. In these cases, the non-uniformity requires two-dimensional or even three-dimensional treatment to be understood properly. So again, I'd urge you to go and have a look at Sims. He talks a little bit about the maths associated with this, and there are other papers out there which talk about this. And this is actually an area that's received relatively little attention compared to planar waveguides. But it's something I think which is quite interesting. And as we go to more and more smaller and smaller micro optics and also micro holograms for storage, these types of analysis become more and more important, especially as we try to pack these things together. Due to the infinite beam width, the output will be badly distorted in this case. This is A, okay? So we have a beam coming in, and suppose this is finite, yeah? And we replay a grating. So we have a grating here that was made with infinite beams, and now we replay it with a finite beam. And what's going to happen? Well, the light's going to come in here, and it's going to be scattered in this direction. Perfectly uniform grating. But what's going to happen here eventually is that as we move further and further up here, we're going to separate from this beam. And at every point along here, we're going to get generation of light diffracted in this direction. But the strength it's diffracted with, yeah, the amount that's going to be diffracted is going to change, because as this beam travels up here, it's losing light. So although it's on Bragg, down here we have 100%, if you like, so we have strong diffraction from this grating. But as we move further and further up here, we have less and less light in the input beam. And therefore we're going to have less and less of the light diffracted, okay? So we're going to produce an output beam which is not going to be uniform in intensity as a function of the spatial frequency. So finite beams and infinite gratings give rise to a whole set of issues, okay, that we have to be aware of if we use a finite beam to replay an infinite grating. We're going to get, if you'd like, diffraction effects, which in a sense are produced by the fact that we have a finite replay beam. So a finite beam width output will be badly distorted. In this case, the input wave must be decomposed into an infinite spectrum. So we have to treat the input not as a single plane wave, but we have to write out this finite beam as an infinite set of plane waves, which are replaying this infinite grating. And if we do that, we can actually find out what's going on. We can actually predict what comes out on the other side. We have to decompose the input into plane waves, because this finite beam can no longer be well represented by an infinite plane wave. The boundaries of the grating may not be simple. In fact, the grating is totally independent of the volume boundaries. So we have a situation here where we've got a grating here, where we've got two finite beams, and that's going to produce something which is going to be finite inside the layer. And as we go to more and more extreme situations, that finite grating structure is going to look different. So we have an interference pattern between these two finite beams, producing something like this. And again, to really explain what's going on here, we have to describe this finite beam as an infinite set of plane waves. And this finite beam is an infinite set of plane waves, producing a set of grating components which vary, and they're going to vary depending on position. And again here, we would not say we have a finite grating inside the triangle. We would say the grating is probably strongest inside this triangle, but we'd actually say there's actually grating components everywhere, because we've got a set of infinite plane waves due to these finite beams coming in here, but this would be the strongest region. And the same sort of a process would apply here, where we'd have an infinite spectrum here, an infinite spectrum here, producing an infinite set of K vectors, and we'd have a particularly strong grating in this finite region. But we can think of this here, if we look at this, we could imagine, for example, replaying this at various input sides or ports, okay? So we can deal with these using infinite plane waves, but the maths gets a bit tricky, and there's other things that can be done. Two-dimensional coupled wave theory can also be used, and so these two mutually differential coupled equations are necessary. It can be solved, so we can reduce it down, and we can actually come up with a two-wave solution based on a finite grating type structure. Equations are to be solved by numerical methods using a 2D mesh. That's another way. In crystallography and integrated optics, several unusual results, what's called Borman effect and beam squeezing, have been examined using combinations of finite beams and curved boundaries. So people have produced volume gratings where they input a plane wave, okay, with a certain finite width. So we could imagine a certain number of centimeters. And the light comes into a grating structure, which may be finite. And what you get out is a beam, a single beam, and that single beam is much narrower. Okay, so you put in a broad beam into a grating, and you get out a single beam, and the extent of it is much smaller. Yeah, and you get quite a lot of light into that beam. So you compress the spatial extent of the beam using these finite structures. Now, that's quite interesting. Okay, and again, there's something in Sims about this, and you can go and look at the literature. And sometimes these things are best described using the mode type structures that exist. This grating can only be examined accurately using 2D theories, okay? Yeah, these types of two-dimensional elements, this will be a lens. So this would be an on-axis lens. So you've got an interference pattern between, for example, a plane wave and a spherical beam, which is converging on this point. So you'd have a converging beam and a plane wave, and they will produce a set of fringes like this. And as you can see, this slant, yeah, the periods in X and Y vary either side here, and we can have an off-axis lens. Okay, so we could have a point source. We could be focusing down here somewhere. We could be focusing from a spherical beam somewhere in another position, or we could have a plane wave coming in at some angle and being focused at this point. And we can have multiple lenses in the same layer. So we could have a beam coming in, producing a set of points, set of focal points at different locations. Typically, the more complicated the element, the less the diffraction efficiency. I think there's a lot of work that can be done there to improve this. But you need a two-dimensional theory to analyze this. Yeah, in particular cases using columns and thickness. So it's complicated, okay? So here's our plane wave, here's our spherical converging beam, and that produces this result here. We replay and we produce a spherically converging beam. So it would probably be good to put in these spherical wavefronts, which will converge to a point, and of course, then they'll diverge. And of course, there's going to be achromatic effects here that if I record with a particular wavelength, if I change that wavelength, I'm going to get blurring, okay? Typically, this type of element wouldn't necessarily be used much for imaging, but it would be used for power transfer, okay, just to get power in a particular thing. So focal length, then the lens can be modeled as an array of uniform grating. So one of the things that people do here is they would say, well, okay, we talked about this idea of slicing, taking individual layers. But even in that case, if we slice in this direction, what we might find is that there's still an appreciable variation along here. So in here, you see you've got quite uniform. So light that comes in here passes straight through. Light that comes up here is scattered down. So another way to do this is to actually split this up into sections. So you'd have a box up here, which would act like a prism. So it would be a slanted grating. So you put light in here and it's deflected down. You put light in here as deflected with a different angle. Yeah. So some combination of decomposition of this structure into 2D spatial arrangement can be used to analyze this grating. And although it's a quite simple process, yeah, it can greatly simplify and provide insights into what's going on. So in other words, we can decompose this into lamellar sections like this, okay? But we still have too much variation in X. So what we then do is we take slices across here and we say, well, in this part here, we have a particular grating, and that particular grating takes a plane wave and turns it into a plane wave. And then we would feed at each point, would feed that into the next layer. So we'd have a decomposition both in the Z direction and in the X direction. And most numerical methods, that's what they do anyways, effectively. They do a 2D decomposition. So again, we have a summary. We've examined non-uniform gratings, taper and chirp, effects of average index variation, nonlinear recording, very crudely, yeah. We've examined in detail the case of lossy recordings, in particular noting the existence of an effective grating strength, yeah. So we get this average effect that gives us the on-brag. We've also examined chirp, where the period in Z is not a constant. And for the two-wave case, using a section decomposition method with 2x2 matrix multiplications, we qualitatively examined linear and quadratic changes in the permittivity. Yeah, we distinguish between those two, the effects of those two, linear and quadratic chirp, and linear and quadratic variations in the average index. And we said these two are very similar. If we do the models, we find out they're similar. So we've got different physical effects and different values of the coefficients, but the net result is the same. So they're hard to distinguish. We've looked at experimental curve fits, and we said, look, this isn't just, a weird and wonderful thing. We can actually fit experimental data and get halfway decent results. We've discussed our results in terms of the Fourier transform of the cross-section of the grating. So again, this is very hand-waving, and it's an analogy. Yeah, it's an analogy from which we can draw some conclusions. Yeah, and it ties in with things you've done before in signal processing. So it gives you something to think about in this characteristics, especially this idea of a filter and the wavelength filtering characteristics of gratings. And finally, we introduce some other types of non-uniformity, situations where we've got finite gratings, okay? And we replay these finite gratings, okay? And this idea of overlapping gratings and lenses, okay? Now I'm going to talk a little bit about applications. If everybody's okay there, if there's any questions. Are there any questions? Now, again, as I said, there's a lot more detail in SIMS, and you should have access to SIMS now. Okay? So is everybody okay? Are there any questions about that?
I don't see any questions.
Very good. Okay. So then, we're nearly at the end of electromagnetism, ladies and gentlemen. We've got one more thing to do in relation to electromagnetism. And the reason I'm stressing this is because this is well determined, it's well known, this is experience that people have, and all of these things, this is the engineering groundwork to all of the stuff you do when you look at holographic optical elements. You've got to have this stuff in your back pocket. Okay. So we come on to the next one. This is slide number 8, okay? And again, this is our excuse me, this is our background. And again, just to remind everybody that we're coming up on this 50th anniversary and 60th anniversary, which I think are very important dates in the history of holography. And again, all the background stuff from me and a little advertisement work we've done on speckle, where we've actually looked at things like blood flow or veins on plants, and we've been able to determine those things, and also things like fundamental aspects of speckle, speckle reduction and suppression, and also the applications of speckle to metrology applications. So measuring displacements, for example, using speckle. And so all of these things have kind of come together in our work. And of course, when you actually have any real optical systems with coherent light sources, you're going to run into problems with speckle. It's a multiplicative noise, and it's fascinating. Okay. So again, we recall these models that we've been building up. We've been working from the scalar model up to these intermediate type models, and then to the more rigorous models. And we went through and we talked about all these things. And I still want to emphasize to you the strengths associated with these scalar models and how useful they are. Okay, and don't just throw them by the wayside. There are situations where they become very, very useful, and they're very powerful, and they link a lot of what we do and beam shaping into the work that other people are doing, designing with systems, working with systems. Okay, so these things are very useful for figuring out what's going on in systems using ray tracing and things like this. Our intermediate models, where we've got in waves but no second order derivatives, or two waves, etc. And what we're going to talk a little bit about today is the Maxwell's equations, the rigorous case. So this puts the crown on the top. So we started off down here, remember, with our scalar model. We talked a little bit about in wave, first order, yeah, Ramanath type variation. We went to Kogelnik, and we spent quite a bit of time at Kogelnik, because Kogelnik is very, very important, both in characterizing holographic materials and also for analyzing a whole range of these optical components. And now we're going to jump up here to the rigorous coupled wave type theory, okay? So we've gone the full gamut, and each one of these things has advantages. These are less physically realizable. Kogelnik is only two waves and one grating component, and we talked about the need sometimes to have n-grating components or to have multiple waves. And now we come up here. But in all cases with this Kogelnik type method, we ignored our second derivatives. So we ignored our boundary conditions, and we ignored strong coupling. We ignored all strong coupling between the waves and the gratings. So we had finite thickness. So for example, while these are quite interesting, we can't use any of these models, for example, in general, we can't really use them to look at, for example, surface relief gratings, that's for sure, okay? And sometimes in volume case, when you record volume holograms, you produce surface relief patterns. So you've actually got a combination of a volume grating and a surface relief grating, okay? So if we go to something more complicated, if we want to test the accuracy of whatever approximate model we've developed, we have to go to a rigorous method where we keep in our second order derivatives. And again, we're back to this analysis where we have our electromagnetic theory and Maxwell's equations. And we're going to talk specifically now about the diffractive method, the state space method that was used and proposed by Gaylord et al. Mohram and Gaylord et al., which they've developed to a very high level. Okay, but even since then, there have been other developments, and particular for particular types of grating cases. Again, we remind ourselves, we've got diffraction orders in the reflection direction. We've got diffraction orders in the forward direction. And then we've got a representation of the field inside the volume using the flow K expansion. So we describe the field using these plane waves, which have got a modulation of their amplitude. But the grating vectors all obey this flow K expansion. So we've got the input beam plus some integer times the K vector is going to be equal to the diffraction order inside. And then we're going to have to phase match across these two boundaries. So we're going to phase match between medium 1 and medium 2, which means we match our E, tangential E and H fields here. and we're going to inside and outside, and we're going to have to match our E fields inside and outside this layer here. Okay, so we got our second order coupled wave equations. Now previously, what we did in this case when we had the S here, and we've got it in the medium number 2 inside the volume grating. We have a single grating, a single K grating, modulation or average. And what we did previously was we said, okay, we're going to have these amplitudes, which vary as a function of Z, and we have this off-Bragg parameter, okay, and we have a coupling to -1 and +1. So the K vector, and we've got a single K vector, is going to couple any beam, the ith beam here, to the I-1 and the I+1. And that's the way that's how we define it in our two-wave case. Yeah. So first of all, in all the previous examples, we came along and we said that's negligible. We can forget about that, the second order derivative. And if we only had two waves, then basically we'd only have two of these coupled equations. Okay. So we'd have each wave is coupled to the other. We only have two of these. We'd have had an S0 and an S plus or an S minus 1. And this one would be coupled to these two. And we would have assumed, for example, that one of these beams here would be very far off Bragg. But now we're going to retain the second order derivative. And this is the notation now that's very much used by Gaylord in the paper. And Sims talks about it as well. I think Sims use A here instead of S. Okay? And the S0 here would correspond to the R, which we had in the cognac. And this is one of the things people change the notation because they want to emphasize particular points. So how do you solve this type of differential equation? Yeah, so this differential equation, you've got a set of second order coupled differential equations. Well, what you do is you define a parameter which is equal to the term, and you define a parameter which is the derivative of that term, okay? And then you write a vector, and that vector is made up of this term and that term. And you say that the derivative of that vector, which is this, is equal to a matrix times this vector. So this vector here now, as I said, this is S, and this is the first order derivative of S. And we'll have this here multiplied by this here is going to give us the first derivative of that. Okay. So the first derivative of this is that. So you've got 0 and I. This is your unit matrix. And then this here is the second derivative. It's the derivative of that. So this is a second derivative is equal to B times the first derivative and C times, sorry, B times the function and C times the first derivative. And if you go back up here, you see you've got a first derivative here and you've got the function itself here. So if you've got the following matrix form, you can write that this is equal to this multiplied by this, and that matrix is this matrix over here. Okay. So the derivative, we call this then the S matrix. Derivative of the S matrix is equal to A times the vector itself. And so we've written this out here that this is equal to this and this, yeah, now this second derivative by this. And so we have this form. And that there is inside the grating. Okay. And we expanded it out here, that if we actually look at that coupled wave equation, we see we have a zero matrix here, we have an identity matrix here, and this goes on for however, how many of these components we keep in. And here we have something with diagonal matrix, and this A value is down each side, and here we have a diagonal matrix with the C components, where all of these things are defined as follows. If we take that now, we can say, well, we're going to assume a form of solution. Remember before we had our R of Z was equal to a constant times an exponential plus another constant times an exponential for the opposite direction. Well, now what we do is we say, well, we know the form of solution for this is going to be equal to a constant, and that constant Cm is going to be defined by the boundary conditions. So how much light we put in. This here is going to be an eigenvector. It's going to be an eigenvector, component of an eigenvector. And this here is an exponential where this is an eigenvalue. And if you take the matrix and you find out you apply an eigen operation, you can find out an array, yeah, the eigen of that vector would give you the lambdas and the omega, the W in Q. So in other words, we take this matrix, we feed this matrix into MATLAB, yeah, with these particular values. We apply this operation. I just use the MATLAB here. I don't assume you know, it's the mathematics. You can go away and look at that. This would be the form of solution. This is the mth eigenvalue of A, and this here is the eigenvalue element of A. And C are constant coefficients determined by phase matching the tangential E and H components across the boundary at Z is equal to 0 and D. So we're going to have two sets of boundary conditions, one at Z is equal to 0 and one at Z is equal to D. So we have the total reflected beams. So these are the diffraction orders going the backward direction, and these are the transmitted. And we see these KI's here are simply given by the grating equation. Whatever a period is across along the boundary there, in boundary between 1 and 2, we can find out what all those vectors, they're simply going to be determined by the grating equation. And the coefficients, this is our input, and we're assuming it's got a value of 1 here, an amplitude of 1. And these are reflection orders. We want to find out what those are. And this is E3, this is the total field in the third region. And the T3J, there's the diffraction orders in the forward direction. So if we go back up here and we look at this, so these R's are associated with the amplitudes of these, and the T's are associated with the amplitude of these. And this is the incident beam, which we assume has a value of 1. And all of the angles here are going to be defined by the input beam here and the period along the boundary. Again, the replay beam and the period along the boundary are going to give you the angles of all those beams, the grating equation. So we can define these two, and these are sometimes referred to as Rayleigh expansions. Okay, the Rayleigh expansions associated with this. And here, we note here we've simply put in a d times z to indicate that we're on the z is equal to d axis. It turns out it makes things a little bit easier in terms of numerics. Now we're going to have to do phase matching. We're going to have to phase match along x. Yeah. So the kx components here and here, these things are going to have to be equal to this. They're going to be phase matched across the boundary. And along z, we're going to have this matching. Yeah? So we're going to have to phase match the things. In other words, the maxima of the patterns, this individual plane waves, are going to have to match along the boundaries, or else we won't have this time-independent solution. We've assumed we have a single frequency solution. So our boundary conditions, going from region 1 to region 2, z is equal to 0, and region 2 to 3, z is equal to d. Yeah, and recalling this definition that our H field in the x direction is minus j over omega mu, angular frequency, permeability, the rate of change of the E field with respect to Z. So this is for the E field replay. We're going to have the tangential E field and region 1. This is our input beam, yeah, and this is the ith component, and this is only equal to 1 for I is equal to 0, has got to be equal to the S of I at 0. So that's matching the tangential field, yeah. And if we match the field at the outside, we've got each one of these transmitted beams is SI at D times this phase term, okay, is phase term. And for the tangential E field, using this formula, we're going to have that this here, again, this is our input, has got to be equal to this inside the volume, this term inside the volume, where we've got here the SI of 0, and this is a rate of change of S with respect to 0. And for the tangential field, we have this thing here, for region 3 has got to be equal to this in region 2 inside the volume. So we have to solve, we've got expressions, we come back up here, we have expressions here for the S field components in terms of the eigenvectors and eigenvalues. We don't know what the C's are, okay? We also have this requirement for the angles at which these beams propagate. We have to match these tangential components from 1 to 2 and 3 to 4. And we can write this down as a matrix. We can write down the S as a B times X, where this B is 4 by 4. So we can take all these boundary conditions and write them down in this form. And then we can basically solve to find out what the S are. Yeah, we have S components inside, forward and backward propagating. And we apply our boundary conditions. Yeah, and we know what 1 is, and we can find what the S is. And if we know what the S is, we can go away and find out what the transmitted beams are and what the reflected beams are. And if we have as incident power equal to 1, then we can find the diffraction efficiency of the reflected beams, it's given by this, and the diffraction efficiency of the transmitted beams, which are given by this. These are basically obliquity type factors. We've got a normalization with respect to the input power, yeah, and basically we have the output angles. And we may have different refractive indices in the medium 1 and medium 2. So that's numerically how you go about doing that. Yeah, you've got two sets of problems. You've got an eigenvector, eigenvalue problem, and then you've got yourself a boundary condition problem. Now again, this is probably dealt with in best by Costu, but you can go to the Gaylord papers, Moram and Gaylord, and you can see how they actually do this. And they actually not only do this for single layers, but they do this for situations where you've got multiple layers. They would use that, for example, to look at surface relief gratings, where you've got very, very strong refractive index variations, and you decompose the grating into a set of layers. Or, for example, a triangular grating, where you've got to build it up into different layers and then treat each layer separately and then match between the actual layers inside the volume. So they've dealt with quite extreme situations. So it's quite a powerful tool. Now, of course, that dealt with a situation where you had a single grating component. And we talked previously about the situation where we had H gratings, okay? So all of this analysis here, when we look at the coupled equations, these coupled equations, as I said to you, we've got a situation where we're coupling this particular diffraction orders to the diffraction order above and below it. But in the general case, where we've got multiple grating components, we're not just going to be coupling to the ones adjacent to it, the diffraction orders adjacent, we're also going to be coupling to higher orders. We're going to have grating vector components that, for example, not only scatter from S0 to S1, but if we've got 2K, we're going to scatter from S0 to S2. And if we've got a 3K component, we'll go from S0 to S3, okay? So we can have a grating which has got multiple components. And for example, again, this could be a situation where you've actually got a whole load of gratings in coordinate material, or we can increase, we could have a cross-sectional refractive index, which would correspond to having an index of 1.5 in a region. And then in the next part of the period, we could have an index of 1. And this would correspond to a layer in which we have a rectangular grating, where we have a silicon goes to air. So we have a surface relief pattern. We can deal with that, and also surface relief patterns which aren't just rectangular or lamellar, but which are triangular, etc. We can deal with these things using this type of analysis, where now we deal with multiple grating components. And we do very much the same sort of thing. Here's our second order equation. We substitute in for the permittivity. We make an assumption about the form of the field we're going to have with these amplitude variations, and we apply our flow K condition, this requirement on our actual diffraction order. So we're assuming that our E field is best approximated by a set of plane waves inside here, the volume. And we end up with, again, a set of equations where basically this is going to be the same, but now this is going to change. So this is different. This is just a multiple. We're going to have a much more complicated expression. And as a little exercise, I'll send you away to look at Moorham and Gaylord's papers, and maybe to look on Sims and to see what this form is. We've also, if you go back and look at lecture 5, we actually talked about the form of this for a situation where we had H gratings. Okay, so you can go away and you can analyze this and you can see where this comes from, because we're going to have direct coupling to all the various waves. So this is pretty much going to remain the same, but this is going to get much more complicated. Now, that's pretty much our EMAG theory. Okay, that's pretty much our EMAG theory. The next thing I'm going to talk a little bit about is holographic applications. Okay, and why we want to use these holographic optical elements, because you need some motivation. Okay, a little bit of motivation here, and specifically about volume holograms. Essentially, they can be used to, besides metrology, what we're probably mainly thinking about is replacing or supplementing refractive optical elements at this point. And the big advantage of these components is that they're thin. They're very thin and they're lightweight, and you can coat, you can place a coating, you can have a curved surface or a complicated surface, and you can coat that surface with some photosensitive material, and you can record a grating in that position. Now, this sounds like a great advantage. I have to say, it hasn't been done an awful lot in practice, but it is certainly a possibility. And it's something you can't really do very easily with refractive elements to attach them. People have done it, but you can't. The disadvantage, and it's a disadvantage advantage, it depends on the context and what you're trying to do. These elements are diffractive. Typically refractive elements, there will be some material dispersion associated with them. But in general, they work for relatively broad bandwidths. Now, the diffractive elements, we've talked about stacking diffractive elements to actually reduce the dispersion, to make them more achromatic. There's also the issue of anisotropy, and you may want to have something which is polarization selective, but if you don't want to have it, then basically that will be a disadvantage to the holographic optical elements. So, you know, whether you see something as an advantage or disadvantage very much depends on your application. I got a list here of some of the applications we're going to look at very briefly in terms of optical elements. Beam splitters, we've talked about, and they can be polarization sensitive or polarizing beam splitters. Reflectors, the prisms, or beam deflectors. You can use them for multiplexers or demultiplexers. They can be used spatially, or they can be used as wavelength or angular multiplexers or demultiplexers. So there's quite a bit of flexibility there, and I'll show you some examples. You can use spatial shuffle or compression. Okay, and again, I'm going to show some examples of this. And again, these are situations where if you want to do two-dimensional deflections you've got to be careful about your polarization. In coupling and out coupling, so drop add devices, either for planar waveguides or communication type systems, backplanes, and lenses which can be multifocal. And again, pretty much there's a huge range of different applications of these devices. And this is just a basic I'm going to show you some examples of. So diffractive optical elements. So we have here a volume grating, we have a pyramidal surface relief blaze grating, and we have a lamellar blaze grating. And all of these are basically deflection elements, and they all basically replace a prism, okay, a refractive optical element. Of course, I had to go and show the hologram deflecting in the opposite direction to all the others, but it shows there's an equivalence here. And if you've got the period along the x-axis, then basically that period is going to define or determine the actual dispersion, the strength of the dispersion effect, the change of the angle for the wavelength and vice versa that you get for these various elements. And of course, it will depend critically on the period, as I said. And the period will also determine whether or not you've got a thick volume grating or holographic grating. But all of these are essentially diffractive optical elements, and they're all essentially replacing refractive prisms. And the general rule is to keep the model as simple as possible. And this is what I was trying to get across, starting off with the scalar models. Try and use the simplest model you think you can get away with. The scalar model is a single scatter transmittance function. Generally, a lot of the calculation can be done using Fourier transforms. You've got analytic expressions, or they can be done very fast numerically. And in terms of designing a system or looking at the effects in a system, using something like this as a starting point can give you very good insights into where you want to go and what you want to do. But as we said, there are a whole range of effects, especially when you get strong diffraction, thick gratings, where you've got to use and you've got to start thinking about rigorous models, whether these are multiple wave models, with radii expansion, maybe including evanescent waves and boundary conditions, or whether they're rigorous electromagnetic models, integral or differential. Now, again, we did a rigorous model above. We looked at these boundary conditions, and we can have waves inside the volume and outside the volume, which are non-propagating waves. And all that would mean is that we would have the exponential, the phase term in the z direction would be real valued. So the beam would be decaying exponentially. And sometimes you have to retain those evanescent waves. And sometimes you get the wrong answer if you don't. Okay, so just again, surface relief gratings, here's lamellar, we've got just lamellar, you've got the rectangular, and you can have lamellar variation and depth, you can have height variation, you can have periodic variation, you can have two-dimensional surfaces. And all of these will definitely require rigorous electromagnetic modeling because you've got very strong boundary conditions. You can supplement the covalent link with some reflection coefficients, but that's as far as you're going to get. Okay, very simple holographic optical elements. This is a head-up display. It's an off-axis mirror. So you've got light coming in from the top and it's reflected in the forward direction. So you don't have specular reflection. This would be a slanted reflection grating. You can have beam splitting, angular wavelength, polarizing, multiplexing or demultiplexing, where you put a beam in and you get a series of beams out. And basically the grating structure determines the amount of power in each of these beams, but also the actual characteristics of the grating will depend. So for example, you could have a polarizing beam splitter in this case, where basically you just have two beams and one of them contains all of one polarization, or you could have the TM polarization coming through and the two other beams being TE polarized. And in coupling and out coupling to waveguides, where you've got a beam, this first one there is a transmission type element, where you've got a beam incident, and then the diffracted beam is diffracted at such an angle into that waveguide that it's going to be totally internally reflected. And the other one is a reflection element, where you basically have the beam coming down through the top surface, reflected into a diffraction angle. So again, you can see there's some flexibility here. And for example, those elements could also have a lensing action built into them. So they're also focusing the light at some distance. So you can cancel out some spreading of the beam as it propagates down the waveguide. And you've got lenses. And we talked about these in the modeling of these and the fact that they're very wavelength selective. And you can have, and if you've got some non-uniformity, loss of fidelity, you're going to have aberrations. Okay, we're on the hour now, and I'm going to send you out this thing and talk about some of these other applications of these types of gratings and advantages. And then basically, hopefully we've got things motivated, and then we're going to talk a bit about, we're going to go to the materials, okay? Now I've got some information about surface relief gratings. It's really beyond the course. I could mention that stuff if people are interested. because again, they're also volume gratings. They just have strong boundary conditions. But it'll come the next day and I'll roll up this business about the application so you're motivated to see why you want certain characteristics from your material. Okay, we'll stop there now. I think we're exactly on the 2-hour point. Has anybody got any questions?
So let's have a couple of minutes just for the people to ask whenever they want.
Yeah. Any questions? There's a lot of stuff here, you know, and I know I'm going quite quickly, yeah, because there's a lot of material to cover. But I want you guys to have a fairly good, nice, broad picture. And also, in a way, I'm trying to reflect also the historical context of what happened, yeah.
Professor Sheridan, may I ask a question about the rigorous coupled-wave analysis model?
Sure.
If I understood correctly, you made a model which repeats the equations for Gaylord and Mohram in the MATLAB, yeah?
I have, the first time I did it in Fortran 66. So you can use any, you know, to be honest with you, I'm not very interested in software, okay? And I'm not interested in software because I started working with BASIC and Pascal, and you know, so I've been around a long time and use mostly now what I use is Mathematica, yeah. And my students mostly use MATLAB because it's simply so available and it's so powerful. And MATLAB tends to be more powerful on the numerics than Mathematica.
Okay, but actually what I wanted to ask is, did you have problems with the model sustainable when you was modeling some different holograms or different diffractive elements?
Can you say the question again, because it cut out in the middle? Sorry.
Okay, did you have some problems with the model being sustainable?
So when you say sustainable, what do you mean? Do you mean convergence?
Yep.
Okay, so because you have to be very careful with the numerical simulations, okay? In general, this difficulty arises when you have evanescent waves, okay? That's when you have fields which are decaying in the positive Z direction, and if you have fields decaying in the negative Z direction. Because if you simply go forward, what you tend to have is you tend to have very small numbers and very big numbers. And you want to avoid dividing big numbers by small numbers, okay? And this is what typically happens in when you use this type of methodology. What's important, the other issue is if you do TE polarization and TM polarization, because it turns out that in TE polarization, the use of the permittivity is fairly straightforward. But when you come to the TM polarization, you often end up with 1 over the permittivity, okay? So you have to have a new series. So the convergence of the permittivity can change a lot when you go from TE to TM. And that affects, the convergence of the term, which includes the permittivity, can vary a lot. And so that can change. You have to basically include a lot of grating components. And sometimes including a lot of grating components also implies retaining a lot of waves, and therefore you end up with this evanescent problem again, okay? So those two things can hit you, okay? So it becomes very, very important to only retain the waves which physically are important. So waves typically which are not very far off Bragg. That's one thing, yeah? And the number of waves outside the grating, the propagating, so you can have different number of waves outside the grating. You can retain different numbers of waves outside the grating than the number of waves you have inside the grating. Okay, that's important. You don't have to have the same number of backward traveling reflection waves and forward traveling transmission waves as you have the number of waves describing the E field inside the layer. And in fact, in the case of, if you are transmitting if you've got very few diffraction orders, a very small period. So suppose you have in the air, you have 2 or 3 diffraction orders. but then you have a substrate which is glass. You may have more than 3. You may have 4 or 5 diffraction orders in the glass. Now, any wave that's propagating, it's probably a good idea to try to attempt to calculate what power is in those waves. But neither the number of waves in the backward reflection direction or the number of waves in the forward direction actually define the number of waves you need to retain inside the volume. Yeah. So if you're careful, you can try and minimize the number of evanescent waves you retain inside your structure, because those are the things that are going to crucify you in terms of the actual numerical calculation. Yeah. And as I said, the only complication that arises is that sometimes in order to retain enough coefficients of gratings, yeah, you have to actually retain evanescent waves. Now, I know I'm not answering the specific question, because the specific question boils down to, I have a grating and it has the following period and it is between these two media and I'm playing it with this wavelength. How can I get the result to converge? That's the specific question, okay? And what I'm saying is the answer to the specific question, okay, boils down on figuring out how far off Bragg all the waves are. So drawing your EVA diagram, for example, and figuring out how far off Bragg the various beams are. Figuring out, for example, if you've got spurious gratings, you know, what gratings you are there, and figuring out what waves are actually propagating in the medium above and below the grating. And then trying very hard to balance all these things out so that you avoid numerical issues to do with evanescent waves. Now, if you can't, there's 2 approaches that I found kind of useful, yeah? One is that this is now specifically talking about the coupled wave model. You can go away and you can look at something like a modal model. Now, the modal model tends to provide actually a better approximation to the field with fewer modes, okay? But you still have to cross the boundaries and you still have to basically then convert the total field inside to the total field outside. But sometimes the modal method will produce more stable results. The difficulty with the modal method, okay, and with the state space approach is that in both of those cases, you're going to end up with, if you've got anything more complicated, yeah, if you've got a more complicated type situation inside your grating, so for example, non-uniformity or anything like this, you're going to lose flexibility and you're going to have to do a lamellar disk decomposition. So you're sort of, and one of the advantages of lamellar decompositions is you could again have different total fields inside each lamella. Yeah. So you then run into an issue where you've got a physical problem which maybe has some complexity, and you're basically trading off the complexity of the problem or the formulation of the problem against complexity in numerical simulation. So you very rapidly have more and more and more matrices and more calculations to do, which makes the whole thing very, very slow. Yeah. So ultimately, you need to look at your physical situation and the accuracy you need for that physical situation. And I can tell you one little story, which illustrates very much kind of the approach I take to these problems. If you have a surface relief structure, for example, you can coat it with metal. And all of these types of approaches, the differential approaches, they work very poorly for metals, very poorly. But you can derive out models that will do metals, that if they're perfect metals. Okay, you can't use the differential approach, but you can find out what happens for a perfect metal, yeah? And then you can find out, then you can go to a model like this, and you can say, well, okay, a metal has got loss. And what you can say is, well, I know the imaginary part of a real metal might be J times 80. So what I do is I go to my numerics and I take J times 5, and I take J times 10, and J times 15, until eventually the numerical model fails. Because once I've got an imaginary part in there, I'm going to have waves which are decaying. So you do it until it fails. And then you compare the case where you've assumed a perfect metal with perfect reflectivity to this, not to the real metal, but to something which is approaching the real metal. And typically, if you find your experimental results are lying in between the perfect metal and the highly lossy semiconductor, you say, well, okay, I can't actually model the real case, but I've got a convergence. Yeah, I'm converging. You know, the real case is lower than the perfect metal, and it's a bit greater than this imperfect modeling. So you play. Yeah, you try different things. Now, the other thing is I'm not going to talk about integral methods, because the integral methods, there have been integral methods derived for volume holograms, and things like path integral approaches. And Sims talks a little bit about this in his book, but they haven't gained any great popularity. So if you go working in a job, in industry, nobody's going to talk about those methods. They're all going to talk about Kogelnik or rigorous coupled wave, because those simply are the methods that most people have used. But if you go to surface relief grating, there's a huge range of families of different methods and methodologies. There's conformal methods, there's integral methods, there's multi-source methods. And they're all based around these finite meshes. Yeah. So people have used finite meshes to model holograms, but again, it's much more rarely used because there isn't a close link to the physics. This is really the thing. The reason people like the Gaylord method is because it builds on the Kogelnik method. Okay. And I'm going to talk to you a little bit about my non-local method for modeling photopolymers. And I think the reason people like that is because most of the people who use it are people who've done holography, and therefore you've used Kogelnik and they've used Gaylord, and then my method uses pretty much the same sort of numerical type approach with Fourier decompositions. Yeah. So it's easy for people to pick up the idea. Yeah. And there's not, I mean, that's a lot of things are popular for that reason. Just I learned it as an undergraduate, and so it's easier for me to learn it as a graduate. Okay. And to change the approach completely is very, very difficult. Yeah.
Okay, I think I got it. Yep.
Any other questions? So as I said, I've sent around now PDFs, and I hope you all have access. I know one lady had some trouble, Nadia had some trouble, but I think she got access to them. I'm not sure if her name was included in the circulation list I was using. You should also have the YouTube, at least for 3 of them. I understand the one from Saturday isn't available yet. So I hope that'll become available. I hope it hasn't disappeared into the ether. Please let me know what happens. And if I can help at all, I will, you know. In the worst case, I'll give the lecture again. You don't have to be Peter. I'll give the lecture to Vladimir. And basically, then Vladimir can circulate the new YouTube video, okay? But this is hard. I understand this is hard and very difficult. And in some places, I haven't been as clear as I'd like to be, but partially that's because it's complicated. And so I try to make it as simple as possible, and I direct you to Sims if you want more information. Okay?
Okay, regarding the lecture on Saturday, I think that the reason why it's hasn't already on the YouTube is because Saturday is the holiday, so it's the weekend. So, you know, we should wait for about...
No holidays for engineers or married men, Vladimir. No holidays. Only work. Only work. Okay.
That's true for engineers, yep.
But
for not for...
Also for husbands. Also for husbands. Okay, folks. So listen, I hope you're all okay. I hope you're following what I'm doing. If you're not, please ask questions. I think I see you again tomorrow morning. Is that correct, Vladimir? We have another lecture tomorrow.
Yep, just let me check, but I suppose that it's correct.
Yeah. So things are going quite well, ladies and gentlemen. I'm always afraid that I'll have to miss a lecture because something happens. So nothing has happened so far. And so I think we're going very solidly. As I said, we're covering a lot of material now. And now we're going to move on to, after I talk about some of these applications, I don't know if you're interested to hear a little bit about surface relief gratings, Vladimir. As I said, it's not exactly on the course, but it does tie in with some of this modeling stuff. But I can leave that. I can send you some PDFs, but not talk about it. And then we're going to move on to polymer materials. Okay?
If I'm correct, right now we are getting some free time still from the lectures because we have a good speed. So
I think we're okay.
Yeah, I think that the coverage of the surface relief gratings will be great.
Okay, so I'll talk a little bit about that tomorrow, just to give you some ideas, because it's very powerful and there's lots of very clever people working on those. And if you talk to people in industry about holographic optical elements, basically what they're asking you is, how do they compare to surface relief gratings? Okay,
yeah,
so that's a typical compare and contrast. So and the models that we've talked about have been applied in that area. So it is a very nice natural kind of extension. So I'll talk a little bit about that. If you'd like, I mean, again, it depends what you like, but I mean, I have work on optimization, search algorithms. I wasn't going to talk about that, but if you're interested in surface relief gratings, using like gradient or simulation annealing or genetic algorithms. I have a couple of slides I could put up about those as well if people are interested for the design of surface relief gratings. Yeah. It depends. Let's see if people are interested. Yeah, we can put in more. Okay. Okay, very nice to talk to you guys. Yeah, see you tomorrow, please God. Take care.
Yep, see you tomorrow. Have a nice day.
Ciao, ciao. Ciao.
Thank you very much and goodbye.
You're welcome. Yeah. And again, if any questions, just let me know.